Hey, welcome back to the series of webinars on the essentials of the tensor calculus. This is part 2, so let's begin this with a quick review of what we saw in part 1. Part 1, we specified notation. You have a mapping, change of coordinates. X stands for a present coordinate system, U stands for a new coordinate system. We call this the inverse map because the formulas for it require that you know the new coordinate from which you can calculate the present coordinate. If you have functions that take you from the present coordinate to the new coordinate, we'll call that mapping phi. Each map has a Jacobian matrix. We'll use this notation for the Jacobian matrix for each map. Here, these are the elements or the components of a matrix. This is a row index. This is a column index. This is a row index. This is a column index. And it turns out that a tangent vector is a column of this Jacobian matrix. Columns of this Jacobian matrix are what I call natural tangent vectors because they're not normalized. The rows of this Jacobian matrix are gradient vectors. We call them natural gradient vectors because we don't normalize them. The notation for a tangent basis vector has a subscript, whereas for a gradient vector, we use a superscript. And one last fact that we established in part 1 was these two matrices are inverse matrices. Product of these in either order results in the identity matrix, and it is very useful to recognize the fact that these two matrices are inverse. So now let's proceed to the part 2 itself. We remember that the preliminaries that we get from multivariate calculus have been split into 2 parts, and we will pick up today's part 2 with the connection between the natural tangent and gradient vectors. There is a relationship between these vectors with superscripts and subscripts that we want to explore. So just consider 2 collections of vectors that have this property. Dot products are either 0 or 1, according to as whether these indices agree or not. So if you have E upper 1 dotted with E lower 1, 1, 1, 1, 1, you'll get a 1 because I and J would be the same. 2, 2, you'd get a 1. 3, 3, you get a 1. Any other combinations, you'll get a 0. So here I have, for the n equals 2 case, I have a matrix, an array of the 4 possible dot products you can be computing. 1, 1, 1, 2, 2, 1, 2, 2. And if you think of it as really multiplying matrices, then if you put E1 and E2 in this column and E1 and E2 in this row, and you multiply E1 against E1 and E1 against E2, and E2 against E1, E2 against E2, what are you really doing? Let's look at these vectors. Okay? E upper 1, gradient vector. It's a row in the Jacobian matrix J phi. And so these two rows constitute J phi. Remember, the columns are still what they should be. Derivatives with respect to the same variable go down the column. Derivative with respect to the same variable goes down the column. Okay, so these vectors, E1, E2, they're column vectors. Differentiate R, position vector, with respect to the same variable, U1. It's a tangent vector to that coordinate curve. Differentiate R with respect to the other independent variable. Get a tangent vector along the second coordinate curve. These two columns constitute the columns of J phi inverse. You want to write these things compactly, you can write them compactly. When you multiply this stuff out, this times that, you get these familiar sums, right? You sum on this index, 1, 1 here, that's going to give you a 1. 1, 2 here, that's going to give you a 0. 2, 1 here, that's going to give you a 0. 1, 1 here, rather 2, 2 here, that's going to give you a 1. This is what the products look like if you take away the sum sign and you put a plus sign in place. And I'm suggesting you get 1s and 0s, which is what I'm saying up here. Vectors that have this property are called reciprocal. What vectors have this property? Tangents and gradients. That's probably where the idea came from. Tangents and gradients form a set of reciprocal vectors. They have this property. Now, so far if you've done Calc 1, 2, 3, you have probably not seen anything except orthonormal systems of coordinates. Polar, cylindrical, spherical, Cartesian. The basis vectors that are used are orthonormal. They're orthogonal. If you have an orthonormal set of vectors, it is self-reciprocal. That's why you may not have seen this prior to a study of tensor calculus or differential geometry. Why are orthonormal sets self-reciprocal? Let's look at it first this way. Let's take two sets of vectors that are reciprocal. Look at the tableau that you have to think about. Put the upper scripts as row vectors here. Put the subscripts as column vectors here. Multiply formally. Take all of the dot products. You'll get the Kronecker delta. That's if you start with vectors that are reciprocal. Now, let's take vectors that are orthonormal. And so I'm just going to pick subscripts. So replace these vectors with the subscripted vectors, because you only have the one set, because we're looking at a set of vectors that are orthonormal. Now you multiply the same formal products, you get these dot products. But these are orthonormal, so because of orthonormality, these dot products will be the Kronecker delta. And so we've just established that if you have orthonormal vectors, they are self-reciprocal. And that's probably why, if you've never heard of reciprocal vectors before, you haven't heard of them. So now we want to think about what happens to tangent basis vectors when you change coordinates. And this is just linear algebra. This is something that you would have seen in a linear algebra course. So question is posed. Find these coordinates, alpha, beta. They are coordinates for a vector v. V is expressed first in terms of the existing basis. And I'm taking the existing basis vectors to be Euclidean I and j. And so the coordinates in that system are little a and little b. So these are new tangent vectors, EU, EV. So I'm using u and v instead of 1 and 2. Thinking in terms of coordinate curves where the coordinates are u and v. And this is a reminder, okay? You want to have something like this tableau in mind. Phi inverse. X is a function of u. Jacobian matrix. dxi, duj. Forward mapping. Phi. U is a function of x. Remember, you have x, that's where you are now. You plug those numbers in and you get a u. That's the new place. And so the Jacobian matrix J phi has elements, components, dui dxj. So let's do the relevant calculations. So here is the position vector. You get new basis vectors along coordinate curves. They're subscripted because we're taking tangent vectors. And what will they look like? They will have two components, dx du and dy du. And the basis here is still I and j. And here's EV, dx dv, dy dv. And so you have an equality. AI plus bj has to be the same vector as alpha EU plus beta EV. Exactly what you do in linear algebra. If you write this matrix product, you're getting alpha times dx du and alpha times dy du. So this matrix product takes a linear combination of this column and this column. That's what this matrix product does. And this is something that you should come out of linear algebra with, understanding that matrix times a vector is really a linear combination of the columns of the matrix. So you're taking a linear combination, but this column is EU and this column is EV. Just look at the terms. XU, XV, YV, XV, YV, okay, and XU, YU, right? So that linear combination is this. And it has to equal, coordinate-wise, AB. But we would like to know these two coordinates. So let's just invert this matrix, bring it over here as inverse, and you have a recipe, a formula. There's a transition matrix here. You have these coordinates now. You make a change of coordinates, and you want to know the new coordinate values. There's your transition matrix. So, transition matrix. Do you recognize that this matrix is really the Jacobian matrix for the inverse transformation? That's why I put it here as a reminder. The x du, right? The x du, the y du. That column is the first column of the Jacobian matrix of the inverse transformation. And this is the second column. And we have to invert that. But we spent a bunch of time making it clear that the inverse of this matrix is this matrix, this Jacobian matrix. And here's a fancy way to express that. And so what did we just learn? New coordinates. That's what this symbol means. New coordinates. If you change variables, is a Jacobian matrix. Right? It's a Jacobian matrix. That's what that guy is. times the old coordinates. Now, row, column. Row index, column index. This sum is across column. This is going across the column. This is coming down. That's what this product is. Now, my major professor used these primes a lot. Some books will say, just use a different name. Put an I over here. Put an I over here. But there are cases where you run out of letters. And so the use of the prime means this is just a different index. If you have a K on this one, you put a K prime on this one. It just keeps the number of letters you got to deal with smaller. So this box is the transformation law for tangent vectors. And it's called the contravariant law. Now, why is it called contravariant law? Well, I've seen explanations on the internet. Here's the explanation that one of the graduate students that I was in graduate school with came up with. Look at this matrix product. The Jacobian matrix is on the left. The vector is on the right. In this setup, if you think in terms of the Jacobian matrix, the sum is from the Jacobian matrix upwards to the vector. Sum is upwards. And he said, against gravity, contravariant, contragravity. It worked for me. And 50 years later, I still think the same thing. Contravariant law. Well, clearly, now we want to look at the transition matrix or the transformation law for gradient vectors. And so we'll pose the question the same way. What are the coordinates, alpha, beta, for a vector, ai plus bj, in a new basis of gradient vectors? Remember, gradient vectors, we use superscripts. Again, useful reminders. Phi, inverse, and phi. X is a function of u is a function of x, Jacobian matrix of the inverse transformation, dxi duj, and of the forward transformation, dui dxj. What are the relevant calculations? Well, what is the gradient normal, gradient basis vector? dx du, dy du. The function stays the same and you need the two derivatives. The function stays the same, v, and you need the two derivatives. And so you equate the vector in the one basis with the vector in the new basis, which is a linear combination of these two vectors. And you can represent that linear combination as a matrix product. Now, this vector appears here as a column vector, u sub x, u sub y. So here is something you want to pay attention to. The array appears ux, uy, appears as if this were a row, but over here you have to stick them down as a column. So there's a hidden transpose lurking in here. This is EU, this is EV. You solve for alpha beta, and so you have inverse of this matrix. What is this matrix? Let's examine what that matrix is. It is the transpose of J phi. Because in J phi, for it to be a Jacobian matrix, the derivatives have to be the same in each column. It has to be an x derivative going down this column and a y derivative going down this column, but you don't have that. The x derivative is the same going across. So you have that hidden transpose. So there is J phi transpose, and you have to invert that matrix. Now the transpose and the inverse commute. You can switch the order of transpose and inverse. So now we have the inverse of J phi transpose. But the inverse of J phi is J phi inverse. But that matrix, that Jacobian matrix, still has that transpose. Remember, there's that hidden transpose that sneaks in from here, and it's still here plaguing us. How can we deal with that? Let's write this whole statement transposed. So this column vector becomes a row vector. This column vector becomes a row vector, but you have to change the order of the product. This we have just recognized as the transpose of the Jacobian matrix, but now I'm transposing that, so the transpose has gone away, and I have a transformation law for gradient vectors that has the old vector on the left and a Jacobian matrix on the right. Now look at that sum. From the perspective of the Jacobian matrix, that sum is downhill, co-gravity, covariant. There's the name covariant. So the covariant law is for vectors expressed in terms of gradient vectors. And the contravariant law is for vectors expressed in terms of tangent basis vectors. That's what this stuff means. And I think at this stage it would really help to have some examples. So let's look at a few examples. Here's one in polar coordinates. And I'm going to use Maple. And here are some notational devices. And I'm going to use its vector calculus package. And I'm going to invoke the gradient command in the student vector calculus package. I'm going to apply it to a function of r and theta. And I'm going to tell Maple we're working in polar coordinates. And here is what the gradient looks like in polar coordinates. You have an r derivative and a basis vector and a theta derivative divided by r and a theta basis vector. These basis vectors are unit vectors. They are not the natural basis vectors. These components that are in parentheses are called physical components. That's how these are distinguished in the literature, called the physical components when you work with unit basis vectors. But remember, what we have been working with, what we have been describing, are the natural basis vectors. The natural tangent vectors are you just differentiate, and the natural gradient vectors, you take gradient vectors, you do not normalize. So if you would work this out, what is the pair of natural gradient basis vectors? you have to take the gradient of the function root x squared plus y squared here, and the gradient of the arctan y over x here. So this takes the gradient, and I'm switching back from x and y to r and theta. That's what the eval does, makes the substitutions. And I'm doing a simplify where Maple will not know that r is to be considered positive, so that's what the assuming positive says, and I get this vector. Now this is a unit vector, so this and that agree. Well, when you take the gradient here of the arctangent function, you get a 1 over r. This is not a unit vector. That's a unit vector. This is not a unit vector. You see that 1 over r? If you swing this 1 over r under here, then you've got this basis vector. And so using the natural basis vectors, the gradient is derivative with respect to r, derivative with respect to theta. There isn't any of these scale factors showing up because the scale factor has been subsumed into the natural basis vector. And we will see eventually that the generalization of the gradient vector is simply the derivatives with respect to the coordinates in whatever system you are. And here you've been trained to think that, oh, there are these scale factors, and the gradient in these different systems has all other stuff. Here, look at spherical coordinates. Again, if you take the gradient in spherical coordinates, where I like to use rho instead of r, Maple defaults to r phi theta. I prefer rho, so I have to name my coordinates. And see what you get. You get a derivative with respect to rho. The derivative with respect to phi has a scale factor, and the derivative with respect to theta has a different scale factor. If we use natural basis vectors, you would have derivative, derivative, derivative. The scale factors would be subsumed into the basis vector, which would then not be unit vectors. And what you would have is the natural basis vector orthogonal to the rho surface is the same as this unit vector here that Maple uses. The one orthogonal to the phi surface has 1 over rho, has that scale factor times e bar phi, which is Maple's unit vector. So if this moves under here and it's subsumed into here, then you have this basis vector, and all you have as the component in the gradient is the derivative. That's all that shows up. And then with respect to theta, if you look at what E theta is, it's 1 over rho sine phi times this unit vector. So if you subsume this scale factor up into here, then you have just the derivative with respect to theta as the component. Okay, so let's now verify these statements here. And do that by computing the appropriate gradient. So I take the gradient of rho, the rho function, but rho is the root of x squared plus y squared plus z squared. Now, to keep the expressions a little bit more compact, I have defined x, y, and z in spherical coordinates. So if you remember your spherical coordinates, this is the mathematical definition of spherical coordinates, where phi is the angle measured downwards from the z-axis. It goes from 0 to pi downwards from the z-axis. Theta is 0 to 2 pi around the z-axis. Physicists switch those two names. Engineers too. They switch those two names. Math books, this is typically the description. Okay, so E rho is this vector. This vector is that vector because it's unit. Differentiate phi. Well, what is the phi function? If you look at the diagram for spherical coordinates, one way to express it is z over rho. And rho is root of x squared plus y squared plus z squared. So you carry out this computation, you let people know that rho is positive and phi is between 0 and pi. You get this. You see the 1 over rho? Okay, there's your 1 over rho coming out. And if you do the same thing for theta, well, what is theta? It's arctan y over x. You take the gradient with respect to x, y, z. See here, when you take the gradient, the variables are x, y, z. You don't have to say that the variables are x, y, z. But here, there's only two variables. If you didn't say x, y, z, Maple would put a 0 for the third component, or wouldn't even compute a third component. But you can't use del and then give coordinates. So you have to use the gradient command itself, and you say x, y, z. See the 1 over rho sine phi, 1 over rho sine phi. So there's your scale factor that shows up over here. In general, what are we saying here in general? Well, we have a function of the independent variable, f of x. X, in turn, is a function of new variables, u. Now, when you make this substitution, you don't see any more x, y, or z. You see u, v, and w. And the things that you do to x, y, and z are not the things that you do to u, v, and w. You might square x, but you might cube u. And so it's a different function. If I put the hat on it, it's related, but it's a different machine acting on the variables u1, u2, u3, or u, v, w, however you want to think about it. And if you continue with this same process and you replace u with u of x, then you have only x, y, and z, and that function is the original function f of x. And this is a basic identity we want to start with. And here's it in the case n equals 3. F of x1, x2, x3 is some new function, related but different, of u of x1, x2, x3, u2, x1, x2, x3, u3, x1, x2, x3. I want to differentiate this with respect to the chain rule. So df dx1, let's just think about that one. df dx1. How do you do that? It's df hat du1 du1 dx1. That's this term. Plus df hat du2 du2 dx1 plus df hat du3 du3 du1. And you do that now with respect to x2. Pattern is the same. df hat du1 du1 now du2. df hat du2 du2 dx2. dx2, where you had a dx1, you now have a dx2. And then down here, where you had a derivative with respect to x1, you have a derivative with respect to x3. x3, x3. Now, these are common. They can be pulled out and written as a matrix times a vector of derivatives on f hat. I wonder if we can recognize this matrix of derivatives. dui dxj, dui dxj. But there's a transpose lurking in here, okay? Because for this to be a Jacobian matrix, these derivatives have to be all the same down the first column. So this is really a transpose of j phi. So let's transpose this. This that we want to transpose is column vector, is j phi transpose vector. If you transpose, you will get this is the gradient vector expressed as a row vector. This becomes a row vector, and this becomes the Jacobian matrix for the transformation phi. But we would like to know the transformation law for this vector. So let's pull it out, solve for this by multiplying from the left with the inverse of this matrix. Now, the inverse of this matrix is j phi inverse. Right? We've seen that several times. We established that. And so what we have is the new gradient vector is the old gradient vector multiplied on the right. Covariant law. You recognize the covariant law here? This is gradient vectors transformed by the covariant law. Sum is downhill. Cogradient, cogravity. Row vector expresses gradient vectors. That's the reason for having row and column vectors. It's because column vectors by convention are used for tangents, and row vectors are used for gradients. They're different. They form reciprocal sets. They have two different transformation laws: contravariant, covariant. Notice that when you take the gradient in the new system, no scale factors. The gradient vector is just the tuple of partial derivatives, because the scale factors are absorbed into the natural basis vectors. And that's really where they're hiding. They're hiding in the rows and columns of the Jacobian matrix. And we'll conclude this section with a brief summary. Tangent vector. The coefficient has a superscript, but the basis vector, tangent basis vector, is a subscript. Transformation law has the Jacobian matrix to the left of the vector. The sum is uphill, contravariant. This is really the Jacobian matrix of the forward transformation. For a general gradient vector, so you're taking linear combination of the gradient, natural, basis vectors. The coefficients have a subscript. Vectors have a superscript. Transformation law has the Jacobian matrix on the right. The summation, from the perspective of the Jacobian matrix, is downhill, cogradient, covariant. And the matrix, the Jacobian matrix here, is the Jacobian matrix with the inverse transformation, Phi inverse. So that concludes our look at what essentially comes from a course in multivariate calculus. And that's the first third of our program. In part 3, next webinar, we're going to look at the tensor object itself, basic manipulations that you can perform on it, and that means we're going to end up looking at the metric tensor and the idea of raising and lowering indices and what does that mean. Now, the material for parts 1 and 2 will be made available to anyone who contacts me by email, rlopez@maplesoft.com, rlopez@maplesoft.com. If you've already got the material for part 1, you just dump it, because I'll send you parts 1 and 2. So if you're going to continue, you probably want to get that stuff and have it at hand, go over it before the next webinar.